Now that you know how the Excel's random number generator works, now I could show you how to use it to generate the numbers for our random variables. First, let's take a look at the direct labor cost, C1. It has a discrete distribution. So we have 5 possible values, 43 through 47, and with the associated probabilities. So this is kind of like the coin toss problem. In the coin toss problem, we had 2 possible outcomes, heads and tails, and each had the probability of 0.5. Here the difference is we have 5 possible outcomes instead of 2 possible outcomes. But we could use a similar method to generate the values for the labor cost. Like in a coin toss problem, we could assign specific intervals to the possible labor costs according to their probabilities. So for instance, 43 probability is 0.1, so the length of the interval corresponding to 43 must be 0.1. So if we start at 0, then we could go to, let's say, 0.1, and so this interval would correspond to value of 43. So if we get a number between 0 and 0.1 from the rand function, then we generate 43 for the labor cost. Okay, what about 44? It should have probably 0.2. So starting at 0.1, we would go 0.2 this way to come up with the interval. So it's about, let's say about here. And if the length of the interval is 0.2, where this one was 0.1, then the interval should end at 0.3. So between 0.1 and 0.3 would correspond to 44. 45 should have interval of length 0.4. So going from 0.3 and going 0.4 from 0.3 gives us 0.7. That corresponding to 45. Then 46, length of the interval is 0.2. So from 0.7, we go up to 0.9. That's length of 0.2 for 46. And the remaining interval 0.9 to 1 would correspond to 47. The intervals we came up with here are called random number intervals. So random number intervals. Let's write these down. So the first one goes from 0 to 0.1. Second one goes from 0.1 to 0.3, 0.3 to 0.7, 0.7 to 0.9, finally 0.9 to 1. Now in the 10 trials model, you could see how it's arranged. The intervals are arranged like this: 0 to 0.1, 0.1 to 0.3, 0.3 to 0.7, and so forth. So the lower random numbers and upper random numbers have the separate columns. So these are your random number intervals, and here are the cost per unit, 43 to 47, and the random numbers we use are given here. And here we're going to generate the appropriate number for the labor cost. Now this simulation has 10 trials. So now let's go back over here and try to guess how many times each value will occur out of the 10 trials. That is, compute the expected frequencies. Well, for 43 should occur about 10% of the time. Now, out of 10 trials, that would mean 1 time. 44 should occur about 20%, which will be 2 out of 10. 45, 4, 2, and 1. Okay, and then after we simulate, we will see what we actually get from the simulation. So later we're going to record in this column observed frequencies. Okay, are you ready? Okay, random number 0.9109. Which interval contains 0.9109? Well, it's right here, between 0.9 and 1. So the direct labor cost here would be 47. So that's 47. 0.2841 is between 0.1 and 0.3. That gives us 44. 0.6531 would mean 45. And 0.0367 is between 0 and 0.1, giving us 43. In a similar fashion, we could put in the rest of the column. Now let's count the frequencies for these possible values. Okay, 43 occurred only once. 44 occurred twice. 45, you got 1, 2, 3, 4, 5 occurred 5 times. 46 occurred 1 time, and 47 also once. Now I'm going to copy this over to the observed frequency column in the other sheet, right over here. You could see that observed frequencies are very close to the expected frequencies. You wouldn't expect the numbers to exactly match, but you expect the numbers to be close, and that's what we have. Now we'll see how to generate the parts cost that has a uniform distribution between 80 and 100. Notice that the parts cost has a uniform distribution just like the random numbers from Excel, like here. So all you have to do is just use a different scale. What I mean is we just draw another scale here that starts at 0 and ends at 1. So this scale would correspond to the random number from Excel, and then we just convert the numbers from here to the numbers on this other scale. So for instance, suppose that you happen to get random number 0 from Excel. Then what parts cost would you generate? Well, the parts cost then would be 80. Okay, now what if the random number happened to be exactly 1? That would correspond to C2 of 100. Okay, now here's a tough one. What if R is, let's say, exactly 0.5? Then what is the C2? Oh, well, that must be halfway between 80 and 100. That is, when R is 0.5 here, then the parts cost should be equal to 90. Okay, what about this one? R equals 0.25. Then, well, let's see. That's halfway between 0 and 0.5. So that's halfway between 80 and 90. Must be 85. Of course, in general, we need some kind of formula to go from the R value to the C2 value. And that formula is given by C2 is equal to, 80, the smallest value of the interval, and then plus the length of the interval, that is 100 minus 80 times the random number. Of course, 100 minus 80 is 20, so the formula is 80 plus 20R. Now, in general, we would call this number A, the smallest number, and the largest number, we call it B. And the formula looks like this. C2 is A plus B minus A times R. Now let's use this formula to generate the parts cost for the 10 trials. Remember, C2 is equal to 80 plus 20 times R. So the random numbers to use are over here. Okay, so here we're going to do 80 plus 20 times 0.2680. And this part is 5.36, so it's 80 plus 5.36 is equal to 85.36. So 85.36. Okay, second, one more for practice. 80 plus 20 times 0.5842 is 80 plus 11.68, giving us 91.68. Now this formula is very easy to apply, so after you've done it twice, you're pretty much an expert. So I think we could stop here. Now the third variable, the first year demand, we're told follows a normal distribution with mean of 15,000 and standard deviation of 4,500, as we could see here. Here, the random number from Excel is a cumulative probability. That is, R is the cumulative probability. So the R is the area under the curve of your distribution. Okay, so that is probability that X is less than some number. And this number is what we are looking for. For example, suppose R happens to be equal to 0.5. Then we'll be asking, what is the number such that probability that X is less than or equal to that number is equal to 0.5. So what is this? So the area under the curve to the left of this number is 0.5. That is, the area here is 0.5. So what is this number? Oh, right, it's 15,000 because it's its normal curve is symmetric, so you know that 0.5 is to the left of the mean, which is 15,000. So then we would say, aha, this number is 15,000. Now let's look at the first trial of the 10 trial simulation. Here we are given random number of 0.7005, and that gives us the demand of 17,366. That's how we get that. Now R is 0.7005, so that would be like past 15,000, and let's say it's about here. So the area under the curve is 0.7005, and what is this number? Now remember, before we usually have the X value, and then we look up the probability, the area under the curve. This time we're going backwards. You could actually do this using the table, but we're going to take a shortcut of using the Excel formula. It's called norm.inv. So you would type equal norm.inv. It represents inverse normal, so that's why it's norm.inv. And there are three arguments: the random number, the cumulative probability, then mean, and standard deviation. So in this example, R would be 0.7005, and mu would be 15,000, and sigma would be 4,500. So we'll try it on this sheet. Even though there was already a number there, we're going to just do it over. It's norm.inv. Then it tells you here what to do. Probability, and the mean, 15,000. And normally, we would want to copy this down to the rest of the column. So the references to these mean and standard deviation should have the dollar signs. So that gives us 17,366, which was already there before. Now we want to discuss the profit calculation. To give us more room, I'm going to hide the random number columns. Okay, remember the profit was equal to 249 minus C1, direct labor cost, minus C2, parts cost, times first year demand, X, minus the $1 million. So let's go ahead and do that. Here we have 249 minus C1 47 minus C2 85.36 times 17,366 minus 1 million. Okay, and remember you need to subtract these first, do the parentheses, multiply by 17,366, and then subtract 1 million. That gives us 1,00525,570. Okay, as a practice, we'll just do one more. 249 minus 44 minus 91.68 times 12,900 minus 1 million is equal to, and you should get 461,828.